you can see that in the case of multi-reaction, you can use the method of equilibrium constant, using the equation to solve for the epsilon, just as we just do. Right? But before you can use the Excel to solve the iterative calculation for you, this one, you have to determine the chemical reaction in the system first. Many considerations until you get the independent chemical reaction in the system. Then you can write the mole fraction, and then you can write the equation which will be the objective function for you for solving. So overall the procedure might be very tedious, and it is difficult for writing the code for computer solving, computer application, computer calculation application. So actually there is another way that you can calculation in the case that you have more than one chemical reaction. So right now I switch to the last lecture right here, number 14.1. So if you remember from the very first lecture slide about the chemical reaction equilibrium, I have ever shown you this figure here, which show that if you have any chemical reaction which is not in the equilibrium yet, the total gift energy of the equilibrium will change in the direction that the gift energy decreases, like this. And when it reaches the minimum point, at that point, it is the equilibrium reaction coordinate. And at this point, you can see that, you can say that at this point, the total gift energy is minimum. Or the other way, you can say that the slope of this point equals 0. The slope in the mathematics means the differential of the total gift energy versus the equilibrium constant, reaction coordinate equals 0. So it gives us two criteria for the chemical equilibrium. The first one is the total gift energy should be minimum at equilibrium. Another one is the differentiate the total gift energy by the reaction coordinate at the equilibrium should be equal to 0. And from this criteria, we use this one, the differentiate the total gift energy by reaction coordinate at specific temperature and pressure equals 0 as the criteria, fundamental criteria to solve for the equilibrium constant. Here, so this is the previous lecture slide. Relation between the gift energy and reaction coordinate. We use the fundamental property here to get the differentiate between the total gift energy and reaction coordinate, which equal to the summation of the stoichiometric number of species multiplied with the chemical reaction. And with this one, if we consider at the equilibrium, it means that the root term here should be equal to 0 from this one. And at that time, so we get the new relation of the summation between stoichiometric number multiplied with the chemical reaction. Summation for every species should be equal to 0. This one becomes the criterion for the chemical reaction equilibrium, which derived from the differentiate of the total gift energy by reaction coordinate should be equal to 0. And from this one, this relation, we got to use to derive for the chemical, the equilibrium constant here, which we have used so far. If you remember this equation, which we have used so far, the reference side here equal to the equilibrium constant. This is what we use so far. So And you can see that the method of the equilibrium constant that we use the second criteria here can be used for the single reaction and also the multiple reaction. But in the case of multiple reaction, it might be a little complex, as you can see in the exercise 2 that we done before. So actually, in the general, in more common way, when you deal with the multiple reactions, there is another way that you can directly calculate the mole of species at the equilibrium, which is using the methods of the total gift energy minimization. This one is come from the first criteria of the equilibrium. At the equilibrium, the total gift energy should be minimum. So if we can write the total gift energy as a function of the mole fraction of the mole of species or the reaction coordinate, and we can minimize that function by changing the reaction coordinate for the mole number, then you can get the value of the epsilon at the equilibrium where the total gift energy is minimum. And this way is very far more common when you have many chemical reactions in the system. In order to use the gift energy minimization, you have to we consider the equation a little bit. When you have many chemical reactions and you don't know which reaction will occur first. It's just simultaneous reaction. So the analysis, the traditional calculation using the relation between equilibrium constant and viscosity might be complex and very tedious. So another way that you can use is the minimization of the gift function of the system. Because we know that at the equilibrium, the total gift energy should be minimum. In order to do that, actually the total gift energy is equal to the total mole number in the system multiplied with the total gift energy in the system. And this term should be equal to the mole number of species I multiplied with the gift energy of species. And then summation for every species in the system. This is equal to the first. And from this one, you can, the gift energy of species will, in the system, will be equal to the standard gift energy plus with RT natural log of fraction between viscosity in solution and standard state viscosity. So in this case, from this one, you just rearrange or specify, clarify the relation here, and you get this equation. So the meaning of this equation is the total gift energy. This term is equal to the total gift energy will be equal to the summation of the mole of species I multiplied with the standard state gift energy of species I. Sum for every species, plus with RT and multiply with the mole of species I times with the natural log of the viscosity in solution over the standard state viscosity. Sum for all species times with the RT and times with the third term. The both term here is equal to total gain. So it means that if you can find the value of the Ni here, that makes this equation is the minimum value. It means the Ni that you can solve in that case is the Ni at the equilibrium already. Just a little rearrange a little bit in the case that you deal with the gas-phase reaction. So in the case of the gas-phase reaction, you can change the viscosity viscosity in solution into the term of mole fraction in gas phase and the viscosity coefficient like this. This is the same. and the standard state viscosity will be equal to standard state pressure in the case of the gas. And another one is this standard state heat energy of species I here will be is equal to the standard given energy change of formation of that species. And this one standard given of formation is exists only for compound, but for the element there will be no value of the standard state of formation here. As I said before, the element does not have the formation reaction, only compound. So with this consideration here, in its gas phase reaction, we change the viscosity in solution and standard state viscosity in terms of the white eye, the white eye and the P here. Then from this equation, you get the equation number 1 here. So in equation number 1 is the total given energy as a function of temperature and pressure at the specified temperature and pressure will be equal the first term of the summation of the standard given of formation of every species, and the second one is the term of the natural law of pressure, and the third term is the summation of the natural law mole fraction in gases for every species, and the last term is the summation of natural law of viscosity coefficient for every species. We can distribute like this because from the mathematics, the natural log A times B equal natural log A plus natural log B. So this one from multiply like this is become the plus term. So for the minimization of given energy method, you can use the equation 1 as the objective function. What you need to do, the problem is you have to find the set of the mole for each species that minimize equation 1 here. But one thing that you have to add for the objective function here is you need constraints from the material balance to to get the correct answer of the mole fraction of the mole number. So the constraining equation in the total given minimization method from the material balance is look like in number 2 here. This one is even though when you have many species in many chemical reactions, the balance of the chemical species is not constant when in and out. For example, in as water, the mole number of water at the inlet should not be constant or should not be equal the mole number of water at the outlet. However, the total number of atoms of each element should be constant. I mean, when you consider as species, it will not balance. But if you consider as the atoms that at the inlet and outlet of the reactor, in that case, the element should be constant. So the constant mean equation in this method, so we will consider as the element or atom in the system. This equation is the summation of the mole Ni here is the mole number of mole of species I at the equilibrium. How is the Aik here? Aik here is the number of atoms of the K element present in each molecule of chemical species. The K here identified as a particular element or atoms, and the AK here is the total number of atomic mass of the K element in the system, which we will determine from the initial concentration of the system. Let's see the example. So if you have the system of species containing between the methane and hydrogen here, with the initial mole number equal 1 and 1. 1 mole for methane, 1 mole for hydrogen here. The small letter A for species methane in the element carbon is equal 1 because in the methane it contains only 1 carbon atom, whereas it contains 4 atoms of hydrogen. The column here is the element 3. Same for the hydrogen here, the small letter A for species hydrogen, the carbon atom is equal to 0 because there is no carbon atom in the hydrogen. But they have the A hydrogen equal to here. What about the capital A letter here? The capital A is the summation, the total number of atomic masses of that element, which we have to determine by the initial number of mole as well. So the carbon here, which the AC here will be equal 1 times with 1 and plus with the 1 times 0 here, which in total is equal 1. Whereas in the case of AH here is equal 1 here, initial mole number in the methane times with the atom of hydrogen in the methane, which is equal 4, plus with the initial mole number of hydrogen times with the hydrogen atom in the hydrogen, which is equal to. So in the final you can get 6 for the AH here. So in summation, when you use the minimization method of the heat energy for solving, you will have only 2 sets of equations. Number 1 is equation 1 here, which will be the objective function. And the second set is the constraint equation. So far we use the solver without using the constraints. And this time we will use the constraint equation in the solving as well, which the constraining equation is come from the material balance of the elements in the system here. Okay, so as simple as it is, so you just set the equation 1 as objective function and you put the constraint equation, which the number of the constraining equation equal to the number of elements exists in the system. So for example, in this one, you have carbon atom and hydrogen atom, so you will have 2 constraining equations for the carbon and hydrogen atom. Yeah, and this is just the method that we use so far when using the solvers. So, okay, so let's see the example together, see the problem statement together, and then we will have a break and I will let you to think by yourself how to solve this example. So in the exercise, the last exercise that we will do for the multi-reaction equilibrium is here. In this case, we will use the gift energy minimization method to solve this one. If you can see, it's very similar to the exercise 2 that we did before. You have a system that's consisting of the different species here, which is the methane, water, carbon monoxide, carbon dioxide, hydrogen. At 1000 Kelvin, 1 bar, every species is in the gas phase, and at the initial state of reaction, you have 2 mole of methane, 3 mole of water, and they also give you the standard gift energy of formation for each species. So, yeah, I will let you think during break how to solve this one by using digit as your organization. And this is the solution answer when you assume this uh, exercise as the ideal gas state, which is justified because the pressure is only 1 bar. Okay. We will have a break until 10 minutes more. So 35 to 35, we will come back here and we will do the exercise together.